Today's lesson is a continuation from the lesson before on radians, arc length, and angular speed. We're going to focus today mostly on finding radian measure, the arc length, and angular speed in application problems. The radian measure, theta, of a rotation is the ratio of the distance traveled by a point at a radius from the center of the rotation to the length of the radius r. So some vocabulary that are the same is the measure of rotation is the same as radian measure. And arc length here is also the distance traveled by a particular point from here to here where the radius is the same. So let's find the measure of rotation in radians when a point 2 meters from the center of rotation travels 4 meters. So we're looking for the measure of rotation, or theta. We know that the measure of s at which it travels is 4 meters, and we know the distance starts at the radius is 2 meters. So when I plug in 2 for r and 4 for s, we see that the radian measurement is 2. Find the length of a circle of radius 5 centimeters associated with an angle of pi thirds radians. So we're looking for this particular piece. We want to know what our arc length is. So let's solve for s by multiplying each side by r. We do know the radius. It's given by 5 centimeters, and we do know the angle at which we travel in radians to be pi over 3. So when I plug in 5 for r times pi over 3, we end up with approximately 5 and 24 hundredths centimeters. Linear speed in terms of angular speed. The linear speed v, so notice the v here, of a point from our distance from our radius, from the center of rotation, is given by the linear speed is equal to the radius, or the center of rotation, times angular speed. And angular speed is given in radians per unit of time. So I added a little ditty here that the angular speed is equal to theta over time. The units of distance for the linear speed and for the distance of our radius must be the same. W, our angular speed, must be in radians per unit of time, whatever that unit of time might be. The linear speed of an Earth satellite. An Earth satellite in circular orbit 1,200 kilometers high makes one complete revolution every 90 minutes. What is its linear speed? And we're going to use 6,400 kilometers for the length of radius of the Earth. So I have a little picture here for us with some information. We know that time is 90 minutes, and we can complete one revolution, or 2 pi, so we're going to have to convert it to radians here in a second. We want to know what is the linear speed, so I need to know a couple other things in order to find that linear speed. We need to know the radius in order to do so. So it's telling us that we have a satellite above Earth. It's giving us the radius of the Earth is 6,400, and I know this is out of proportion, but then just to get a visual of what it looks like here. And the satellite is 1,200 kilometers above the Earth. So our total radius that we are going with for this satellite is actually 7,600 kilometers for our radius. So let's get to work here. So we need to know and work with the formula linear speed is equal to our radius times our angular speed, but our angular speed needs to be in radians per minute. Currently, it's in just minutes here, and we just know it goes 360 degrees in 90 minutes. But 360 degrees we know is the same as 2 pi. So I can transform this into radians by multiplying or creating the ratio of 2 pi. It makes 2 pi revolution in 90 minutes. Reducing our fraction, we can go pi over 45 minutes. And now we can substitute the rest for our linear speed since we're trying to find linear speed. We know the total radius is 7,600 kilometers times the angular speed in radians per minute is pi over 45 minutes. Multiplying, we see we have 7,600 kilometers times pi over 45 minutes gives us approximately 531 kilometers per minute is the rate at which it's traveling. Angular speed of a capstan. An anchor on a Navy vessel is hoisted at a rate of 2 feet per second as the line is wound around a capstan with a 1.4 yard diameter. What is the angular speed of the capstan? So if you're not quite familiar what a capstan is, I grabbed a photo here just to get an idea of what's happening. They're taking this rope here and they're winding it in a circular pattern around this capstan to hold those ropes. With that, then, I grabbed a visual of the rope coming around in a circular pattern, in a linear pattern. We can find some information here. Now, this is not the correct angle, but just to get us an idea of what's going on here. We do know some information. We do know the linear speeds. It says it's hoisted at a rate of 2 feet per second. So we know the V. We know the linear speed at which it's moving. We also know the diameter of our capstan, but we have to be careful. We're looking for radius with our formula. So we are given diameter. We'll need to find the radius. Further, we're looking for angular speed, so we are also trying to solve for W. Okay, so keep all those in mind. We still are going to use the formula linear speed is equal to the radius times angular speed. We first need to find the radius and we need to find the linear speed, which we are given. The units of distance must be the same. Okay, so keep that in mind. So right now when I look at the radius, we know that we can find radius by taking the diameter divided by 2, which is 7/10 of a yard. But notice we're in feet with our linear speed. So let's transform our yards to feet. And we know that there are 3 feet per yard. So 3 feet per yard times 7/10 of a yard gives us 2 1/10 feet. Okay, so now that we know our radius and it's in feet, and we know the linear speed, which is in feet per second, we can now find the angular speed. So we start with our original formula and solve for angular speed since that's what we're actually looking for. We can divide both sides by r, so angular speed is equal to the linear speed divided by the radius. So angular speed is equal to 2 feet per second over our 2.1 feet. Notice I just kind of moved this along here to put feet over second is equal to 1 over 2.1 feet. We see the feet cancel. When we multiply and divide, gives us about 0.952 radians per second because angular speed is in radians per unit of time, and our unit of time here is in seconds. A 2014 Toyota FJ Cruiser is traveling at a speed of 70 miles per hour. Its tires have an outside diameter of 30.875 inches. So we're going to have to transform that into radius. Find the angle through which the tire is turning in 10 seconds. Not just 1 second or per second. We want 10 seconds, how far it's traveling. We do have the formula that angular speed is equal to theta over time, or we can find the angle, which is the angular speed times time. the distance and time must be the same units. So here we're in inches, here we're in miles per hour. So let's start with working with that, the V portion. Let's convert 70 miles per hour to feet per second so that we can put it into seconds, and then we can transform some of this information into feet as well. So right now I have 70 miles per hour is equivalent to 1 hour and 60 minutes. 1 minute is the same as 60 seconds, and there's 5,280 feet per mile. Notice our miles will cancel, our minutes will cancel, our hours will cancel, and we're going to be left with 102.667 feet per second. Now we know the V. We can also find the radius, but let's transform our radius into feet, since then we'll be in the same unit of measurement. So we'll have the diameter divided by 2, which is approximately 15.4375 inches. We know that in 1 foot there are 12 inches, giving us 1.29 feet. So we're in feet here, we're in feet per second here. Now we can solve for W. We can find W. We can plug in our 102.667 feet per second for our V, which is our linear rate, is equal to 1.29 feet, which is our radius. We can divide, when we divide our feet cancel, giving us 79.59 per second. Now, that is per second. We particularly have 10 seconds we're interested in. So we need to multiply this radian into multiplying by 10 so that we get 796 radians in 10 seconds. One gear wheel turns another, the teeth being on the rims. So I've got the gears here with the teeth being on the outside. The wheels have a 9-inch and a 5-inch radii, so we know the radii between the both of them. And the smaller wheel is rotating at 48 revolutions per minute. Find the angular speed. So we're looking for W of the larger wheel in radians per second. So regardless that one is bigger than the other, the speed at which they're turning is the same. The little one will appear, it'll go around a lot faster than the bigger one, but they're still traveling at the same speed together. So although we have the linear speed is 5, our radius for our small wheel, times W, which is our angular speed, and that's what we need to find. And the linear speed is equal to 9, the radius for the larger one, times W sub 2. So that'll be our second speed for angular speed. We know that their linear speed is the same exact, so we can simplify and solve, setting them equivalent to one another. We do know the revolutions per minute, so we can find the W of the small wheel because we know it's 48 revolutions per minute. Let's turn that into radians per second since we're interested in finding per second and we need radians. So we can plug in 48 times 2 pi. We know that it does 1 revolution, so 2 pi around in 1 minute. That gives us 96 pi in 1 minute. Converting that minute to seconds, we have 1.6 pi per second. So now that we know what the W is for the small, we can find the angular speed for the larger wheel by plugging in 1.6 pi per second, multiplying and dividing, and we see that that second wheel is traveling at an angular speed of 2.793 radians per second. So slightly faster, it's going angularly than the smaller wheel, but that's to be expected. Now their linear speeds will stay the same, whereas their angular speeds are slightly different based on the size.